Hello, everyone. Welcome back for Digital Computer System Architecture. This is lecture 4, part 4, data forwarding. So we're going to discuss how to use data forwarding to address the data hazard, okay? So still use the previous example, right? So we have the R2, R3 added together and put it in R1, and then R1 is used for subtraction and or XOR, right? So data forwarding. If you remember, we have the execution, the output from the execution is already done at the end of the third stage, right? Then basically at the end of the ALU, we can actually forward the output to subtraction and then to and then to or definitely to this XOR because it's already finished, right? So how do we do that? How do we actually solve that problem, right? So first, let's see how we solve it. Basically, what we need to do is we need to have some wheres, like either from go to the source register 1 or go to source register 2 at the end of the execution. This actually allows us to forward data from the execution stage to the beginning of instruction decoding, right? And then we can also have the wheres to forward data from the memory, okay, from the memory to instruction decoding, okay. We can also forward that to execution here, right? So basically at the end of the ALU, see here, or it should be end of the memory access, like here, okay. Or I read back, definitely it's already read back, right? So we have the third stage, end of the third stage, end of the fourth stage, we can do forwarding, okay. With that, you can see at the end of the third stage, right? This is this part, this arrow is exactly happening here, here, or here, okay. And then this arrow from the end of memory, right, is here. Okay, going back to also here, going back to the instruction decoding, the beginning of instruction decoding, right? So that's why, for instance, at the second instruction, relying on the output of R1. So then we do that here. And then the third instruction is also relying on R1. So we do it here. For the second instruction, load the data of R4, and then we store R4 back. So we also do the forwarding from this part to the memory. Since calculating the address, this one is happening in ALU, so that's why this forwarding goes here. And then using this value for store happens in memory access. That's why the forwarding from the second instruction to the third instruction happens here. Okay. Well, even data forwarding is good. It's also important for us to understand that it's likely the data forwarding might not be able to solve the problem. For instance, in this load from R2 as the address, R2 registers value as the address plus a 0, and store it in R1 for this one. It loading, you know, that everybody knows that it only happens after you finish the memory access, right? But for the using of R1, it happens at the end of instruction decoding because you have to fetch the value from the register file when you're doing instruction decoding. So clearly, this happens one instruction earlier, or even two instructions earlier. So we say there's still some instruction data dependencies. But for this third instruction, which uses R1, it can be okay because once you finish this instruction, you immediately pass it to this instruction, right? And for this OR instruction, it's also fine. So we say only this instruction has a like a data dependency that's not being satisfied by the data forwarding, but this instruction and this instruction should be fine. So if this is the problem, what we're gonna do is we're gonna insert a bubble here at the middle of the instruction. Because of the bubble here, okay. This is very interesting. Because there's a bubble here, so the second instruction occupies the instruction decoding phase. For example, the ID/EX pipeline register is occupied by this instruction. Then this instruction also have to suffer from a bubble. Because why? Because once you finish instruction fetch, it cannot go to instruction decoding. Because when it goes to instruction decoding, it has to use this IDEX register files, the intermediate registers. Well, that's already being occupied by the second instruction. So the third instruction has to also be bubbled. And this is a chain reaction because the first instruction occupies the instruction fetch. Sorry, the third instruction occupies the instruction fetch components. Then this instruction also has to suffer from bubble, right? This is how it works. Okay, so one exercise for you guys to deal with is that we want you guys to deal with some software scheduling to avoid loading hazards or data hazards. So what we do is we load B to register, C to register, to addition of RC, RB, and get RA. Then we store RA back to the address, and then we load E, load F, do subtraction and store back. So clearly, there is some problem here because the addition of this one might not, or the load of B and C might not be may not be fast enough for you to directly do like addition, or we say there might need to insert a bubble here, right? A bubble here. So how do we solve this problem? Can you use 15 minutes to think about how to do software scheduling to do that? Okay. All right, so welcome back. So what we're gonna do is very simple. We basically load RE earlier, right? And then store the RA later, so that the bubble of loading RC for this instruction is being filled by this load. And then the load of RF is the bubble afterwards is being filled by the store. Okay.